Good afternoon again. Okay, now we can continue with other examples. Okay, we continue with this example. We have a wheel is composed of a 10-kilogram hoop stiffened by 4 thin spokes. So we have this hoop, its mass is 10 kilogram. We have 4 spokes to stiffen this hoop. Each of these spoke has a mass of 2 kilogram. A horizontal force of 40 Newton. This force is applied to the wheel. Okay, I was disconnected again. Do you have my voice now? Okay, sorry for the interruption. Okay, so we continue. We have this hoop with 4 spokes on it. Each spoke has a mass of 2 kilogram. A horizontal force of 40 Newton is applied to the wheel initially at rest. Calculate the angular velocity of the wheel after its center has moved 3 meters. So the center of this wheel will move 3 meters horizontally, and friction is sufficient to prevent a slipping. So again, in this motion, we don't have a slipping. Okay, so we have again a rotation without a slipping. The problem is similar to the previous problem. Again, we can use different methods. It's up to you. You can use the Newton's second law to find the acceleration, and then by using the acceleration, you can find the velocity of the wheel. But here we use the work and energy equation. We can consider these 2 pairs of the spokes as one, and we can consider 2 connected spoke. One is here with mass 4 kilogram and length of 600 millimeter, and the other one is this spoke, consists of 2 spokes with mass again 4 kilogram and length 600 millimeter. Okay, so we can write the work done by the external force. Again, if you plot the free body diagram, we have the weight, we have 2 reactions here. Similar to the previous problem, the work done by the external force will be just only due to this 40 Newton. We neglect the friction force and the normal force in the work done by the external force in this term. We will have 40 times by dA, which A is this point, which is the 40 Newton force is inserted on the wheel. So dA, again, according to the geometry of the problem, you can conclude that the displacement of point A is equal to 2 times by the displacement of point O, which point O is the center of this wheel. So the work done by the external force is equal to 240, because we know that D naught or DO, or the displacement of the mass center, is 3 meters. So 2 times by 3 meters is 6, and times by 40, which is the work done by the 40 Newton external force. We have the T sub 1, or the initial kinetic energy. It's again equal to 0 because the system starts at rest. The final kinetic energy, or T sub 2, is equal to the kinetic energy of the spokes and the kinetic energy of the hoop. So the kinetic energy for the spokes, both of them are rigid bodies. Yes, so both of them will have 2 portion in the kinetic energy, one due to the rotation and the other one due to the translational motion. For the spokes, if we consider, we will have half times by mass of the spokes times by the velocity of the spokes squared, and plus half times by the mass moment of inertia about the mass center times by omega squared. And we have two coefficients here, as you can see. This 2 is due to the number of the spokes, because here we have 2 spokes. So we will have a coefficient 2 here. And for the wheel, we will have half again times by the mass of the hoop times by the velocity of the mass center of the hoop squared, plus mass moment of inertia of the hoop about the mass center times by omega squared. You know that IOH is the mass moment of inertia for the hoop, and the hoop is similar to the ring. And for the spokes, we can consider them as a cylinder rod. So you can obtain the IO and IO for the spokes and for the hoop. The velocity of the mass center of the spokes and also the mass center of the hoop is the velocity of this point O, because the mass center of the spokes and the mass center of the hoop, for all of them, are located at this point O. If you, of course, if you assume these two spokes as a whole spoke, as a one spoke, okay? If you consider that these two are connected to each other and consider them as only one spoke. And also for these two spokes, again, if you consider these two are a connected spoke and they are only one, so the mass center is again located on point. Okay, do you have my voice? I don't know what's the problem today, but I don't know, it's from my side or from the internet, I don't know. Okay, we can continue. Okay, so we have, you can use the, similar to the previous example, you can use another form of the kinetic energy. I mean, you can write the kinetic energy instead of about the mass center, you can write about this point C. If you write the kinetic energy with respect to this point C, here instead of half mv squared plus half I omega squared, we will have half times by I about C times by omega squared. But it will be a little complicated, because if you want to obtain the mass moment of inertia about the center C, you should transfer both of the mass moment of inertia to this point, and um, it will increase the number of calculations. So here we can use this equation about the mass center, and we can write them. So the velocity of the mass center for the spokes is equal to the velocity of the mass center of the hoop, and it's equal to r omega, because we don't have a slipping in the motion. The mass moment of inertia about the point O for the spokes is, as I told you, it's similar to. Okay, I think the Zoom is becoming similar to the big blue button, and it's connect and disconnect. I don't know what's the problem. Maybe do because these days Zoom is very busy, especially the USB Zoom, the version that we are using. Maybe this is the reason. I don't know. Maybe this is from my side, from my internet. Anyway, I'm sorry again. I was disconnected. Can you hear me now clearly or not? Is my voice clear now? Is my audio clear now? Do you have my audio now? Can you hear me now? Okay. It's really exhausting. I don't know if it will continue this condition. We cannot use Zoom similar to the big blue button. I don't know what should we do for these remaining weeks. Okay, let's continue now. So here we have the kinetic energy, and we can obtain the velocity of the spokes and the hoops by using the r omega, which r is the radius and omega is the angular velocity. The mass moment of inertia about the mass center for the spoke, as I told you, it's because similar to the slender rod, it's equal to 1 divided by 12 times by m times by l squared. And the l, the length of the spokes, is equal to 2 times by r. And the mass moment of inertia for the hoop is, for the hoop, as I told you, it's similar to the ring. It's equal to mr squared. So we can substitute and simplify and obtain the kinetic energy in the final position in terms of r and omega. We want to obtain this omega as an unknown. So we need to obtain the potential energy as well. The potential energy in this term is not considered here. Can you tell me why? Do you have my Audi now? Okay, so can you tell me something or give me some idea about this? Here in this equation, we don't have the potential energy. What's the reason? Do you have any idea? Here we have the work done by the external force. We calculated here 240. We have the kinetic energy in the initial position, which is 0, and the final kinetic energy, but we don't have any potential energy. What's the reason? Do you have any idea why we neglect the potential energy in this equation? Exactly, because the height is constant, so the potential energy is 0. So here we neglect this. We have the work done by the external forces. It's equal to the kinetic energy. And from this term, we can obtain the angular velocity for the system after 3 meters moving in horizontal direction. Okay. So finally, this example has been finished after 4 or 5 times disconnecting. Okay. No question from this example. The value for R is the radius of the hoop. I think it's in the problem description. Let's back here. This is the radius. R is 300 millimeter or 0.3. Here we have on the figure. Clear? Okay, so let's move to the next example. Here we have the sheave of 400 millimeter radius has a mass of 50 kilogram and a radius of gyration of 300 millimeter. The sheave and its 100 kilogram load. Here we have another load which is 100 kilogram mass are suspended by the cable and the spring which has a stiffness of 1.5 kilonewton per meter. If the system is released from rest with the spring initially stretched 100 millimeter, determine the velocity of O, this point, the center of this ship, and after it has dropped 50 millimeters, so it will come down for 50 millimeter. So the change in the height is 50 millimeter. Here, clearly, we should use the work and energy because we have a spring, and the best option is again work and energy equation. So we can solve this problem using the work and energy, and we need to obtain the kinetic energy, potential energy, and work done by the external forces during this motion from this position to 50 millimeter downward direction motion. So the first step, we need to obtain the kinetic energy and potential energy. If we assume that this system released from this position with the initial stretch of 100 millimeter in the spring, we can assume that this system is rotating about this point A. Okay, so after releasing this system, will rotate about point A like a pin connection, and it will have a pure rotational motion about this point A. Okay, so now we can write the energy and work equation. The work done by the external force is equal to 0 because if you plot the free body diagram, there is no external force, only we will have the force due to the spring. Here we have this force due to the spring, and we have the weights, and both of them will appear into the potential energy. The initial kinetic energy is equal to 0. And if we assume this is the initial position is the datum level, so this is the datum level for the gravity. So the initial potential energy is just the potential energy due to the spring. It's equal to half kx squared, which x is 100 millimeter or 0.1 meter. So V sub 1 or the initial potential energy is 0.005 times by K, which K is the stiffness of the spring. Now we need to obtain the kinetic energy. The kinetic energy in final position is due to the translational and rotational motion. So the translational part will include the translational of the sheave and this 100 kilogram mass. So we substitute MT here into the equation. You can see MT is the total mass of the sheave and this mass. So we will have half MT times by VO squared, which VO is the velocity of the mass center, plus half times by IO omega squared, which IO is the mass moment of inertia about the point O or about the mass center times by omega squared. This IO is the mass moment of inertia for this sheave about its mass center, and omega is the angular velocity of the sheave, but this VO is the velocity of the center. You can see that into the rotational kinetic energy, we only consider the kinetic energy due to the sheave because this mass can be considered as a particle, and it has only a translational motion. So this mass will only appear into the first term, which is the translational kinetic energy. But the second term, which is the rotational kinetic energy, will just depend on the rotation of this sheave, because only this sheave will have rotational motion. So we can substitute VO is equal to 0.4 times by omega, as I told you, because this system will rotate about this point A as a pure rotational motion. So the velocity of point O is equal to 0.4 times by omega, and it depends on the angular velocity. So you can substitute into the kinetic energy and extract the kinetic energy as a function of omega, which is the angular velocity of the sheave. So the next step, we need to obtain the potential energy in the final position. The potential energy in final position will be will include the potential energy due to this spring, and the potential energy due to the change in the height or the gravity potential energy. The spring is equal to half k times by x squared, which this time x is equal to the initial stretch, which is 0.1, plus now this point B will go down. When point O will go down by 50 millimeter, the point B will go down by 2 times by 50 millimeter. Okay, so x is equal to initial stretch, which is 0.1, plus 2 times by 0.05 or 50 millimeter, which we converted into meter, and finally it must be squared. Okay, so we will have half times by kx squared. And for the gravity potential energy, because it's the final position is under the datum level, so it will be minus mt, which is the total mass, times by g times by 0.05 or 50 millimeter. Okay, so this is the final position potential energy, and it's equal to minus 43.5. And this is negative because, as I told you, the final position is under the datum initial datum level. Okay, now we can substitute into the energy and work equation. W is equal to 0. So T1 plus V1 must be equal to T2 plus V2. We have T1 is 0. V1 is the initial potential energy due to the initial stretch, which was 0.1 meter. We have the kinetic energy, which is obtained here in terms of omega. And finally, the final potential energy in the final position. From this equation, we have one unknown, omega. You can easily obtain that omega at this moment is equal to 1.89 radian per second. Okay, clear? Any question? Okay. Okay, the next example, we have the 100-pound uniform circular disc with its attached 20-pound slender bar is released from rest. Sorry again, I was disconnected. Okay, let's continue. Okay, we have the last example. I hope we can finish this with this internet. Okay, we have the 100-pound uniform circular disc. Can you hear me now? Is it my voice clear? Is my voice clear now? Okay. We have so a disc and attached 20-pound cylinder bar, which is released from rest and in the position shown and rolls without slipping. Again, this is the point. Here we don't have a slipping on the horizontal surface. Calculate the velocity of the center O, this center O, when the mass center of the bar is directly below the center O of the disk. Again, in this example, we use the energy and work equation to solve the problem. Here you can see this is the final position for the cylinder according to the problem description. We want to obtain the velocities at this position. And this disk is rotating without slipping. So this point C can be considered as the center of zero, instantaneous center of zero velocity. Again, there is no external force. We only have friction force and the normal force, which both of them will not appear into this term because the work done by these forces is equal to zero. The system is released from rest, so T1 or the initial kinetic energy is equal to zero. And V sub 1 again is equal to zero because we assume that the initial position is the datum level for the gravity. Now we should obtain the final position kinetic and potential energy. The kinetic energy is due to the disk and the cylinder rod. As you can see, we have the kinetic energy for the disk, which is equal to half IC omega squared. As you can see, we have only this term because this is a rotation without the slipping. So we can assume that this disk is rotating about this point C and it's a pure rotational motion. So it's equal to IC omega squared, and IC is the mass moment of inertia about point C. For the rod, a cylinder rod, we have a kinetic energy due to the translational motion is equal to msvg squared. And also we have one rotational kinetic energy, which is Ig omega squared. Vg is the velocity of the mass center. Here you can see this is the point G. Its velocity is equal to this length times by omega, and Ig, which is the mass moment of inertia about the mass center for the cylinder, it's clearly equal to 112 over 12 ml squared, and omega is the angular velocity. So we can find Vg, Ig, and substitute into the equation. Vg, as I told you, is this red line times by omega. And this red line is 16 because the radius of the disk is 16 minus 12 times by cosine 45, because this line, let me show you with another color. This green line is 12 times by cosine or sine 45, and the red line, this length, is equal to 16 minus 12 times by cosine 45, and it must be divided by 12 because we should convert it into foot, and finally multiply by omega, which is the angular velocity. Ig is the mass moment of inertia about the mass center for the cylinder, and it's equal to 1 over 12 msl squared. Ms is the mass of the cylinder, and L is the length of the cylinder. The length of the cylinder here in this triangle, you can easily calculate this because in this triangle, if we assume here, this angle is 45, yes? So half of the length of this cylinder rod is 12 times by sine 45 or 12 times by cosine 45, no different. And so it will be 2 times by 12 times by cosine 45. So this is the length of the slender rod, and it must again divided by 12 because we should convert it into foot. And finally, you can calculate the mass moment of inertia, and IC is the mass moment of inertia of the disk about point C. It's equal to the mass moment of inertia about the mass center plus m times by r squared, and this is the mass moment about the point C, or the instantaneous center of zero velocity. So this is the IC, and now we can substitute into the kinetic energy and find them. And finally, we need to obtain the potential energy in the final position. As I told you, this is the final position. As you can see, the slender rod will located here. For the disk, the mass center position is constant, so there is no change in the potential energy for the disk. So it will be again in the final position is zero. But for the cylinder, we will have the final position which is under the initial position. The initial position for this, if you want to find, we need to let me first show you the final position. If we want to calculate the final H, this is the datum level, okay, and we need to find this length. Okay, this length, which is equal to 6, and 6 is equal to half of this 12, because this length is in fact 6. Okay, exactly at the center of the rod. 6 plus 12 times by cosine 45, and plus this length, which this length is again 12 times by cosine 45, and we divided it by 12 because we should convert it into foot. Okay, so this is a V sub 2, or the final potential energy in the final position. And now we can substitute into the work and energy equation. So we will have the half times by IC omega squared. This term is the kinetic energy due to the slender rod, and it must be equal to the final position potential energy. From this equation, you can easily obtain the angular velocity, which is 2.36 radian per second. And to obtain the velocity of the mass center, you know that the velocity of the mass center is equal to r times by omega. And r in this case is equal to 16 inch. We should convert it into foot, and 12 divided by 12. So the velocity of the mass center is 3.15 foot per second. Okay. Any question? Is it clear? If you don't have any question, we can wrap up this session. Okay, thank you for your attention. So tomorrow we will have the tutorial session at 4 p.m. Okay, thank you. And